Hi, this is Mr. Weisfeld. We're talking about the dynamic summative assessment for advanced AP Physics. We'd like to talk through some of these problems here. So, I'm drawing in red here. First question on the quiz was the following. A 20 kilogram box rests on a table. What is the weight of the box and the normal force acting on it? Okay, so the confusing part is this picture doesn't apply to this first question, A. So let's draw this first question, A. You have a 20 kilogram box resting on a table. First, draw a free body diagram. Free body diagram will show you the forces involved in the problem and help you analyze the problem. So the free body diagram for part A says this. You've got a 20 kilogram box. You've got the weight of the box pulling down. That's M times G. And then when it's resting on the table, you also have a normal force pushing up on the box. That's from the table. Those two forces are the only forces on the box when it's resting on the table. And since the box isn't moving, those forces are in equilibrium, so they're equal and opposite. What you can do is you can write Newton's second law, N2L. We'll use that abbreviation a lot in this quiz, so let's just write it all out. Newton's second law. Which says that the sum of the forces, take all the forces and add them up on the object, equals the mass of the object times the acceleration of the object. So in this case, you've got, if up is positive direction, you've got minus mg plus n, right? N is in the positive direction, mg is in the negative direction, equals the mass times the acceleration of the box. Well, in this case, the acceleration equals 0, as we said, because the box isn't moving. In this, which means that this here is 0. So minus mg plus n equals 0. That means that n equals mg. In this case, m equals 20 kilogram box. And g equals 9.8 meters per second squared. So 20 times 9.8. Let's get our little calculator out here. (196). So N equals 196 newtons. That's the normal force, and this N is the units. Sorry if that's a little confusing. And that's the answer to part A. Next part, part B. A 10 kilogram box is placed on top of the 20 kilogram box, as shown in the figure. Determine the normal force that the table exerts on the 20 kilogram box and the normal force that the 20 kilogram box exerts on the 10 kilogram box. Okay, so if this is the picture for part B, we'll write B here, then let's draw the free body diagram for part B. So free body diagram for part B. When I draw a free body diagram, I imagine that I'm cutting through these connections between the box and the other box, and the box and the table. So imagine that those are little cuts. When I do a cut, this is kind of free body diagram technique. I replace any contact with forces. And especially in this case, since the forces are mainly up and down, the boxes aren't sliding or moving horizontally, I got to replace those with forces. So let's say the 10 kilogram box has m1 times g, where m1 equals 10 kilograms. We'll do that just to keep things straight. Then there's a normal force, n1, on box 1. That's the free body diagram for the 10 kilogram box. Now the free body diagram for the 20 kilogram box has the following on it. bigger box, slightly bigger mass, m2 times g. It's a little bit hard to read. Let me erase that. Weight of the 20 kilogram box, m2 times g. m2 equals 20 kilograms. And normal force from the table, we'll call it N2. It's the normal force on box 2, but also Newton's third law, N3L, means that this N1 pushing up on that box is also pushing down from box 1, the 10 kilogram box, onto box 2. There's a normal force. So now we've got a free body diagram for box 1 and a free body diagram for box 2, and the connection between the two is this normal force that's now down from box 1 onto box 2. When we look at this free body diagram here, we notice that it's the same as this free body diagram here. So N1 is the same answer that we had in part A. So A implies that N1 equals 196 newtons. That's what it takes that's what it takes all the time to basically hold box number 1, the 10 kilogram box, stationary against gravity. So now what we have to do is we have to do Newton's second law on box 2, which means sum of the forces, let's do it over here, sum of the forces equals mass times the acceleration. In this case it's mass 2 times the acceleration, mass 2. Once again, we'll say that up is positive direction so that we can get the algebra right. So we'll basically have minus N1 plus N2. N2 is opposite from N1. And then minus M2 times G. All that equals M2, the acceleration of box 2, times the mass of box 2. We'll say again the acceleration of box 2 equals 0, which implies that this term right here equals 0. So when the question is, determine the normal force that the table exerts on the 20 kilogram box, what that means is that I'm trying to solve for N2, so let's keep our eyes focused on that. N2 equals what? If we solve this equation for N2, we get N2 equals N1 plus M2 times G. But that equals, since N1 equals 196 newtons, we've got 196 newtons plus M2, which is 20 kilograms, times 9.8 meters per second squared. All of that equals 196 plus 20 times 9.8 equals 392 newtons. So 392 newtons is the force that the table exerts on box 2. So that is the answer to B. But only the answer to the first part of B. So let's keep going. The normal force that the 20 kilogram box exerts on the 10 kilogram box, that is equal to N1. So the other answer to B is because of Newton's third law, for every force or reaction, N1, there's an equal and opposite reaction. That means that the other part of B is 196 newtons. One way to think about that is that the table acts as book 2 in the first part of the problem, and then box 2 acts as the table in the second part of the problem. In other words, it's always ever going to take 196 newtons to hold that book stationary against gravity. Okay, let's go to the next problem. The second problem was 2 snowcats in Antarctica are towing a housing unit north, as shown in the figure. The sum of the forces FA and FB exerted on the user is north, parallel to the line L. So we have a resultant force that is north. If FA is 4,500 newtons, what is the magnitude of FB? So FB equals what? And what is this resultant force? If that resultant force is FA plus FB. Alright, so the key to the problem is realizing that resultant force is only, so resultant force, only in the north direction. That means that the horizontal components, the components east or west, cancel. We're going to use this fact here to solve for what f of b is, and let's show you how this works. So even though FA, maybe I want to do another color here. Let's try this. Even though FA is going off like this and FB is going off like this, there are components of those two forces. So FA is right here. FB is right here. In order to analyze these forces, we need to know that FA has a component like this to the west, and we know that FB has a component like this to the east. That's in addition, so let's get another color here real quick. That's in addition, of course, to the components they have that are north and north. So, once again, FB has a component here and here. The addition of those two vector components is the resultant force for FB. That's just one force. FA has a vertical force, has a northerly force and a westerly force. The resultant of those two forces is equal to FA. And back to the physical situation, a cable attached to a snowcat is basically pulling at FA at an angle of 48 degrees. Let's put the angle in here, 48 degrees. And a snowcat here is pulling at 32 degrees in that direction. The problem states that they're pulling in such a way that these two horizontal components, the blue components, cancel out. So the way we write that in algebra is, if the horizontal components cancel, that implies that we have to find out that the FA in the x direction plus FB in the x direction, where now I'm basically defining this as x and this is y, equals 0. So what are those components in the x direction? We have to do sines or cosines now. So what component is it if this angle is 48 degrees that's pulling in the x direction? Well, it's opposite, so it's sine. So FA minus FA times the sine of 48 degrees. Because it's in the negative x direction, FA is positive, sine of 48 is positive. I need this number to be negative. Has to be equal to FB times the sine of 32 degrees. Those have to be equal to 0. The only thing I know besides the angles is that FA equals 4,500 newtons. So if I'm looking for FB, I can say, doing some algebra, FB equals FA times the sine of 48 degrees all over the sine of 32 degrees. Take a moment and make sure that this equation here gets to that algebra. That means that 4,500 newtons times the sine of 48 equals, divided by the sine of 32 degrees equals f of b. This is the first part of the solution to the problem that I've determined FB. So let me plug this into my calculator. 1 second here. 4,500 newtons times the sine of 48 divided by the sine of 32. This is 6,310.68 newtons. And since we only have, this would round to basically 6,300 newtons because we have two significant digits in the problem. Two angled significant digits and two significant digits in the force, FB force. Now, when it says, what is the magnitude? All right, so we're working on this question now. Let me change the color here. So magnitude. Magnitude of FB plus FA. Okay, what we said was that these blue components here cancel out, even though I'm pulling in this direction and this direction, because it's like a tug-of-war. These are equal, they cancel out. However, these components here, the northerly components, are not equal. They don't cancel out. So we do some sines and cosines to figure out what those are. It turns out f of b times the cosine of 32 degrees plus f of a times the cosine of 48 degrees, that equals the magnitude of the resultant. So that equals, we'll call it f sub r, the magnitude of the resultant. There's that's kind of hard to read. Erase that. Let me write it big. Whenever you take two vectors, FA with a vector sign plus FB, you can calculate the resultant, FR, of two vectors. The way you do that is by adding the components separately. That's true in any vector problem, right? What we just did is we said that the horizontal components, which we're adding separately, are 0. Boom. We added those components separately here, and we got to 0, and that put a constraint on FB. Now, what I'm doing is I'm adding the vertical components separately. when I do that, I get this equation here, adding the vertical components separately. That's going to give me the magnitude of F sub r, which has only, Fr has only a vertical component. So take a moment to think about that when you add components separately, but some component, horizontal or vertical, is 0, then you have only what's left over, which is a vertical component. So let's write this equation here with the numbers in it. So Fr equals Fb 6310.68 newtons times the cosine of 32 plus 4,500 newtons times the cosine of 48 degrees. That equals, let me plug this into my calculator just a second. 6310.68 times cosine of 32 plus 4,500 times the cosine of 48. All of this equals 8,362.85 newtons. So we'll call that, with two significant digits, 8,400 newtons. So that's the answer to the resultant force. So even though this snowcat is pulling with 4,500 newtons, FA is 4,500 newtons total. And even though FB is pushing at 6,300 newtons, let's put this newton sign there, they're only really pulling effectively in a northerly direction with 8,400 newtons. Imagine if you just were to add those, that's almost 10,800 newtons, but you're only getting 8,400 out. The reason why is because you're pulling inefficiently, right? These guys are wasting some of their energy pulling against each other in a horizontal direction. We kind of know this in our intuition, but the physics also bears it out. So let's go to the next problem. Okay. Person pushes on a 1,400 kilogram lawnmower at a constant speed with a force of 88 newtons directed along the handle, which is at an angle of 45 degrees to the horizontal. Draw a free body diagram, so FBD, showing all the forces acting on the mower. Calculate the horizontal friction force on the mower, and the normal force exerted vertically upward on the mower by the ground. What force must the person exert on the lawnmower to accelerate it from rest to 1.5 meters per second in 2.5 seconds, assuming the same friction force? Okay, so we got some work to do on this problem. Well, let's just start with the free body diagram. Here's my mower. It has a mass of 14 kilograms, so I have 14 kilograms mg down. There's a normal force that pushes up on the mower, and I'm pushing down on the mower at an angle of 45 degrees. So this is the F, and let's draw the angle here, 45 degrees. Also, there's friction. If the mower is moving this way, you assume a direction of motion because friction opposes motion. It either opposes motion that hasn't started yet or opposes motion that's in progress. So let's draw a force of friction here, and we'll call it force of friction, F of F. Your free body diagram needs to have these four forces written on it and some idea of geometry that's going on. It should be fairly clear that these forces here are only vertical, this force here is only horizontal, and this force here has some components. It is not generally correct to draw components. Not yet, or not ever in a free body diagram. So let me just put that here and emphasize it. Okay, so Newton's second law. Calculate the horizontal friction force. Newton's second law says that the sum of the forces, in this case horizontally, we're only going to talk about horizontal forces for the beginning, equals the mass of the mower times the acceleration of the mower. So let's do this. The horizontal force from F is F times the cosine of theta. So F cosine of theta, theta is 45 degrees. F cosine of theta minus the force of friction equals mass times the acceleration of the mower. Now check this out. When I say constant speed, what am I supposed to assume about the acceleration of the mower if it's moving at a constant speed? Take a moment, think about that. If you're moving at a constant speed, that means your acceleration is 0. So this term here is 0. That means that F times the cosine of theta equals the force of friction. So F is 88 newtons times the cosine of theta, which equals 45. Let me write that again here. I'm basically looking at this part of the equation and just writing it over here. The force I'm pushing on the mower, F, times the cosine of the angle, 45 degrees, equals the force of friction. Because the force of friction is the only force in the horizontal direction, in order to move at a constant speed, all I have to do is overcome that friction force in order to be moving at a constant speed. Now I know what you're saying, but wait a second, how did I ever get moving? Well, it was a different part of the problem when you got moving. The point is, once you're moving, you just have to overcome a certain resistance force, the friction force, to keep moving at a constant speed. Any more than that, and you're accelerating. Any less than that, you're decelerating. All right, so force of friction equals, let's put this into the calculator, 88 times cosine 45. 62.22 newtons. We'll call that 62 newtons for this answer. So, first of all, the free body diagram is right here. Second of all, the horizontal friction force, part B, is right here. And now we're working on part C. Find the normal force exerted vertically upward on the mower by the ground. If you've drawn your free body diagram correctly, this is just N. In other words, N represents the force upward on the mower by the ground. And if I were to draw a free body diagram of the ground, that's weird. We don't normally do that, but because of Newton's third law, N3L says that the force of the ground on the mower is also the force of the mower on the ground. So the ground has a free body diagram that looks just like this. Pretty boring, but also the friction force is pushing against the ground. Makes sense that if the lawnmower were somehow on a mat that could slide on ice or friction, you'd actually be pushing the mat, right? Because the earth has to resist the motion of the mower, the friction of the grass, the drag on the mower. Anyway, this is a little digression. You don't have to pay any attention to that. what I'm basically going to do is I'm going to say Newton's second law, vertically now, is going to tell me what n is. In other words, you're applying Newton's second law horizontally. So you're doing F equals ma in each component direction separately. That's kind of a strategy we use in these problems. So sum of the forces equals mass times the acceleration. The acceleration equals 0 in the vertical direction. So take a moment to convince yourself of that. Since the mower is not moving in the vertical direction, has no acceleration in the vertical direction. So what I've got is F times the sine of 45. That's how much force I'm pushing down on the mower because I'm pushing at this angle. So when I'm pushing at this angle, I'm pushing down a little bit, and I'm pushing this way a little bit. Those are the component forces of the force F that's pushing on the mower. Plus N, and this is a negative force because, it's a negative direction because we said this is positive X direction. Positive Y direction. These are my component directions. This tells me which direction is positive. So this is my X. This is my X direction here. This is my Y direction. So once again, since I'm pushing down, I'm in the negative Y direction, so I forgot a negative sign originally. I apologize. Plus N, and then minus mg. And since a equals 0, that all equals 0. I can solve for n, the normal force, and I get that n equals F sine of 45 degrees plus mg. This is a little unclear here, so let me erase that one line right there. Remember we said the force down on the mower is a negative force. The force up on the mower is a positive force. The force down on the mower is a minus mg. All of those forces combine to give you the normal force that the ground has to push up. So 88 newtons times the sine of 45 degrees plus m, which is 14 kilograms, times 9.8 meters per second squared, the acceleration of gravity. That all equals, let's plug that into my calculator here, 88 times the sine of 45 degrees plus 14 kilograms times 9.8. What I've got is 199.42 newtons. And we've got two significant figures here, so we'll call that basically 200 newtons. $199 rounded to the nearest 2 digits is basically 200 newtons. Alright, so that's the answer to problem C, part C. Part D has a little piece that I'm going to put in a different color. So it basically says the lawnmower accelerates from rest, initial velocity 0, to final velocity 1.5 meters per second. So this is meters per second, in a change in time of 2.5 seconds. What force to get that acceleration? we have to take a moment to think about what is the acceleration given this initial and final velocity and this change in time. So what you need to recall is that the acceleration equals final velocity minus initial velocity divided by the change in time. So in that case, I've got 1.5 meters per second minus 0 meters per second, all divided by 2.5 seconds. This is a little hard to read. I apologize. Let me erase that. This is 2.5 seconds. All that equals 1.5 minus 0 divided by 2.5. That's 0.6 meters per second squared. Okay, so let's go back to Newton's second law horizontally. What we've got is the sum of the forces horizontally equals the mass times the acceleration. The acceleration now is not equal to 0. They just told us what the acceleration is. But we'd like to know what the force is that I need to push on it. So recall this equation right here. I'm going to take this one back. What they just said is, now what's F? This is the angle I'm pushing at. It's the same. This is the same, turns out, and this just changed. So let's do this. This equation becomes force of friction plus the mass times the acceleration, all divided by the cosine of theta, equals the force I need to push at. So take a moment and justify to yourself that this equation here comes from Newton's second law horizontally if you do not assume this time that acceleration is 0. Let me plug this in and show you what I get. I get that F equals force of friction 62.22 newtons plus the mass 14 kilograms times this new acceleration 0.6 meters per second squared, all divided by the cosine of 45 degrees. That's how hard I need to push. Take a moment to think. I need to push hard enough to overcome the friction force, and I need to overcome the inertial force of the mower, how much the mower's mass and acceleration demands to move, to accelerate. But I'm not pushing directly, I'm pushing at an angle, so I need to reduce or increase that force, right, by a certain geometrical factor. So let me plug that. So once again, D, this problem is worked all in blue, and it draws on some previous information. And what I get when I plug that into my calculator is 62.22 plus 14 times 0.6, all divided by cosine of 45 degrees. What I get there is that my force of friction is 99.87, but to two significant figures, my force is 100 newtons. So instead of just pushing at 88, right, the initial problem had 88, I need to push a little harder. So I need to push at 100 newtons. Makes sense. Okay, next and final problem. Okay, we're working on the last problem of our dynamic summative assessment here. And we've got a block On a smooth, frictionless plane that's tilted at an angle of 22 degrees, 22 degrees equals theta in this case. Determine the acceleration of the block as it slides down the plane. And if the block starts from rest 12 meters up the plane, what will be the block speed when it reaches the bottom of the inclined plane? First step, draw a free body diagram. Cut the block free, replace any forces that you need to with, replace any contact with forces. So this is the mg, the block's mass times gravity. And this is the normal force, which is pushing exactly perpendicular to the block, N. You should justify, again, that this angle right here is 22 degrees. In other words, if this plane gets steeper or less steep, this angle here gets bigger or smaller, respectively. Newton's second law says that I can sum the forces in component directions separately. Well, Newton's second law says that the sum of the forces equals mass times acceleration. Let's not muddy the waters first. But what we do, since this is a vector equation, we do components separately. So if we sum forces along the plane, we don't have any force along the plane except mg times the sine of theta. That equals the mass times the acceleration of the block. The question says, what is the acceleration of the block as it slides down the plane? So I want to solve this equation for acceleration. Acceleration equals what? In previous problems, we've said acceleration is 0 for some reason or another. It's not the case here, because the block is going to accelerate. It is going to move. It is going to get faster. So notice that m's cancel. Does not matter how big the block is. Its acceleration down the plane is g times the sine of theta. If g is 9.8 meters per second squared, then acceleration is 9.8 meters per second squared times the sine of 22 degrees, where theta is the angle. If I plug that into my calculator, 9.8 times the sine of 22 degrees, I got 3.67 meters per second squared. Let's say I've got two significant figures, so that's 3.7 meters per second squared. That's the first part of the equation, or that's the first part of the problem. Some people like to remember this, that the acceleration down the plane is just g times the sine of the angle of the inclined plane. You could do that, or you could derive it each time from a free body diagram and Newton's second law. If the block starts from rest, so notice that if the angle is constant, this is a constant acceleration problem. So we go back to our kinematic equations. Constant acceleration. In those cases, the final velocity equals an initial velocity plus the acceleration times the time. Remember, this is the definition of acceleration. These are our kinematics equations. So, kinematics equation. The kinematic equations are true for constant accelerations. That also means that the distance that it travels is equal to initial velocity times time plus 1/2 times acceleration times t squared. And so this is, I call this parabola because it's a second order equation in time, and then final velocity squared equals initial velocity squared plus 2 times a times d, in this case distance, and I call that no time. We don't really care about time in this problem, or it doesn't show its face at all, so it would suggest that we should try no time. So let's take a look at no time first and see if it'll work for us. Notice when we said that when the block starts from rest, we basically said the initial velocity equals 0. Also, when we gave you a distance, it implies that d equals 12 meters. And when I said that I wanted to know the block speed when it reaches the bottom, I'm actually asking for the final velocity. So given that information, it looks like we should use this equation right here. So if this is 0, and we just computed the acceleration, remember this is the acceleration down the plane, I think you could say that the final velocity is the square root of 2AD, which is the square root of 2 times the acceleration down the plane, 3.6711 meters per second squared, times the distance down the plane, 12 meters. Plug that into my calculator, and I get 9.386. 5 meters per second. And if it's two significant digits in the problem, so 9.4 meters per second. So the block will start sliding, and it'll be going about 9.4 meters per second when it gets to the bottom of the slope. So that was the dynamic summative assessment. Thanks for listening.